So, we all have our limitations, and certainly DNA polymerase is no different. Now, DNA polymerase is fantastic at adding nucleotides to an existing strand of DNA to create these new DNA molecules, and we know that it does so adding nucleotides from to the 3' end of an existing molecule. So, if we can imagine DNA polymerase moving in here, it'll attach new nucleotides beginning with that 3' carbon. Well, let's consider when we get to the very end of a chromosome, the situation we have. There can be an Okazaki fragment that's created here that's RNA, but needs to be replaced by DNA. So DNA polymerase can come in and add to the 3' end, but at the very end of the molecule, this is a 5' carbon. So there's no location for DNA polymerase to attach to at the end of our long linear chromosomes. So what happens is when the RNA is removed, we actually have segments on the ends of our chromosomes that are not replicated. So these end up producing what are considered shorter DNA molecules through a process of telomere shortening. Now, this is obviously a better illustration. If we look at the molecule here, here are our Okazaki fragments, here are the RNA primers. DNA polymerase has nowhere to attach at the very end of this strand, so it cannot synthesize in the 5' to 3' direction. So when you remove those primers, you end up with this segment that has no match. So eventually, when this DNA gets passed on, the new strand that's replicated will be shorter than the original strand. So successive rounds of replication create chromosomes that are increasingly shorter. Now, that can be an issue, because if we think, oh my gosh, there are genes on these chromosomes, instructions for making proteins. If chromosomes continue to shorten with successive rounds of replication, eventually we're going to be eating into these genes and potentially negatively impacting the phenotypes of individuals. Now, have no fear, or I guess have reasonable expectations. Good rules to live by. There are telomeres, or these segments at the ends of chromosomes, that do not contain coding genes. They don't have genes for the production of proteins. These telomeres are segments of repeating segments of DNA. So it could be like T, T, A, G, G, G. So there's these repeating segments of DNA at the very ends of chromosomes that are inconsequential, at least in the short term, if they don't get replicated. So they don't have any, again, genes that will be expressed. It's just DNA, some extra DNA. Now, these telomeres will shorten over time with successive replications. So it doesn't stop the shortening. It just helps protect our genetic information by creating these repeated bases that are non-genetic. Now, telomere shortening, it's sort of fascinating if you're interested in the idea of getting older. Telomere shortening is associated with age-related changes, and people are, this is again sort of an area of interest in what happens with this telomere shortening and then this apoptosis or programmed cell death that occurs with everyone. Even in our genetic information, it shortens over time, so death is inevitable. Now, if we think about this, if this happened in germ cells, the cells that create the egg and sperm, over a series of generations, if germ cells lost their DNA, eventually there wouldn't be enough genes passed on to offspring to have a viable organism. Well, there is a specific enzyme that helps with that in germ cells. Telomerase is an enzyme that actually adds those bases to the ends of chromosomes, those sequences, those inconsequential sequences. Telomerase adds those bases to the end so that the telomeres do not shorten. Now, certainly a reasonable question would be, well, shoot, can't we figure out a way to get telomerase to add bases to the ends of our autosomes so that they don't shorten over time and we don't have this natural progression or aging that can occur? Can we extend life by preventing telomere shortening? Well, maybe, but I don't know if we want to do that because there is serious or significant evidence that suggests the shortening of telomeres helps protect us from cancer, because what it does is it limits the number of cell divisions that are possible for a particular cell. Now, if telomeres did not shorten and cells could divide indefinitely, eventually you're going to accumulate enough errors in that DNA to potentially lead to unrestricted or uncontrolled cell growth or cancer. So, by letting cells divide indefinitely, it can potentially lead to unintended consequences like cancer, because again, you can accumulate enough damage or mutations in the DNA to lead to out of control cell growth. And incidentally, there has been some evidence of telomerase activity in cancer cells that live indefinitely. The HeLa cells that were created like in the 1950s, again, those cells live forever, and they have this telomerase activity that prevents the shortening of the telomeres and the death of the cells. So, it's a double-edged sword. Okay.